Hello. Yeah. Good evening, everyone. So I was having some network issue, so that's why I joined a little late. So today is the last tutorial class. This is week 12, assignment 12 of NOC-EE62 NPTEL tutorial class, which is basic electronics. The course instructor is Professor Mahesh B. Patil and myself, Mr. Subhajit Basak. I am a PMRF fellow from IIT Bombay. So, as you all know, the course duration is for 12 weeks, and today it's the week 12, that is the last week, last tutorial class. And like every Tuesday, today also we are starting from 6 to 8. Okay, so at first, let me turn off my camera to get a better bandwidth because some network issues there. Yeah, so let me share my screen. Just a second. Yeah, I hope that it's visible. And yeah, so let's start. Yeah, so we have already studied starting from the basics of the electronics. So we broadly classified these basic electronics courses into two parts, which is analog and second one is the digital. And for the analog electronic circuit, we have learned so far about the basic PN junction diode, and then how the diode can act as can work in a reverse bias, that is a special case of diode which is known as Zener diode. And then after that we moved forward to the basic BJT circuits and how it can work as a small signal amplifier. And then we did some problem regarding the Bode plot, and then we move from the BJT to the op-amp circuit. And in the op-amp we have already studied the negative feedback thing and the positive feedback thing, both the things. In the negative feedback thing we have studied about the summer integrator, all of those. And in the positive feedback we have seen that how this op-amp, the positive feedback of the op-amp can be act as a Smith trigger, and how it can which is basically a bistable multivibrator that is having a two states in the Smith trigger, and how it can act as an oscillator. And after that we move forward, and we move to the second part of this basic electronics, which is digital electronics. There we have studied already about the combinational logic circuit, and in one tutorial and in the other tutorial we have studied about the this sequential logic circuit, which is a D flip-flop and counter and all of those. Okay, so today I will discuss one of the most important thing, that is the ADC and the DAC, which act as a bridge between the analog and the digital circuits. Okay, so let's say so we have a analog signal. Suppose we have an analog signal. So this is some analog signal. So in the environment there is some analog signal, and then basically the processing of the signal is happens in the digital domain only. So use basically processor. More specifically you can say that the digital signal processing unit, digital signal processing unit that can process the signal. So so in the this DSP, that is digital signal processor, it can take as digital signal as an input, digital signal, and also the output is in the form of the digital signal. Okay, so suppose there is some analog signal in the environment. Suppose we want to record some voice, so basically our voice is the analog signal. So then we have to convert it into the digital signal so that we can store or we can process that voice. So this analog and digital, this ADC, analog to digital converter, serves the purpose to convert the analog signal to the digital signal. So here we need A to D converter or ADC, that is analog to digital converter. converter. And again, suppose there is some music stored in the hard disks or in a CD, and then we want to listen that music. So basically, when we listen that music, then it has to be an analog signal at the output. So we want analog signal at the output, right? Analog signal. So basically here also we need one more thing, that is known as DAC, that is the digital to analog converter, which can take the digital signal as an input and analog signal as output. So this DAC means digital to analog converter, digital to analog converter. So this is the basic thing where we need the ADC and the DAC. So I have given the example. So today basically broadly we will study about the some types of ADC, which is analog to digital converter, analog to digital converter, and also we will study about the DAC, that is in the opposite way, which converts the digital signal to analog signal. Okay, so digital to analog converter. So there are several types of DAC and the ADC. Some of the types are for the ADC. For the ADC, we have suppose successive approximation type ADC, and then we have the flash type ADC. So flash type, which is known as parallel. So parallelly it will process this thing. And then we have dual slope ADC, dual slope ADC, and then we can we have studied about the tracking ADC. So all of these things are already discussed in the lecture of Professor Patel. So and counting ADC is also there. Okay, and in case of DAC, digital to analog converter, so most of the two important digital to analog converters are, one is weighted register, and the second one is the R2R ladder circuit, R2R ladder circuit. So we will solve today's example one by one, and we will see that how and we will discuss each of these ADC and the DAC while solving the problem, so that we can get a fair idea about how this ADC or DAC works. Okay, so before that I want to just elaborate a little more thing. So suppose there is some analog signal. So the analog signal, so how we convert the analog signal to digital signal? The analog signal is basically, it is continuous in time and amplitude domain. That means, suppose this is time and this is the amplitude of any signal, analog signal. So suppose analog signal can take any value. Suppose it is one type of analog signal, so it has certain value. It is ranging from suppose 0 to, suppose we can say 8, something like that. Okay, 0 to 8, 0 volt to 8 volt, this signal. Suppose this is V, analog voltage, the VAT, which is depends on time, and this is varying like this, so in the analog signal. And then so how can we convert this analog signal to the digital signal? So most of the two important thing is, one thing is sampling. Sampling means we are sampling, that is we are taking certain after certain time, we are just taking the value of the analog signal and we are plotting that. Okay, so this is some discrete time signal, we can say. By sampling we can get the discrete time signal. Suppose we are sampling here, then here, then here. So like that we are sampling. Okay, this thing, then this thing, then this thing, then this thing, then this thing, and ultimately this thing. Okay, so the sampling time, this thing, suppose it is TS. So after each TS, it's we are sampling the signal. Okay, we are getting that what is the and the amplitude of the signal. Okay, so this is the repeating things. Okay, so after the sampling we are getting the data like this. So suppose there is T, and then this is some amplitude, and now this is some this is discrete time. That is, it is discrete in time domain but continuous in the frequency domain. Discrete time but continuous in amplitude domain. Sorry, my mistake. So it's the discrete time and continuous amplitude, that signal. Okay, that signal. So how we are getting, if we are sampling through this, suppose after TS time we are taking this value. So here it will be like this. Okay, at TS we are getting this value, then we are getting this thing after 2 TS, then we are getting this, and then again some drop like this, like this. Okay, so again some increase. Okay, then again some drop, and then increase like this. Okay, so the signal, the analog signal was like this only, as we have already seen here. This is the analog signal. Okay, this was the analog signal, and we are sampling using the sampling rate, means after TS time interval we are sampling the signal and we are getting this thing. Okay, and then we did the quantization. The second thing is the quantization. Quantization means we are sampling this signal in the amplitude domain. Okay, so after that we are getting certain value, like, so we are getting this dot. So we are just, so it is from 0 volt to 8 volt, as I have already discussed. Okay, so if we just quantized it, so it is one level, it is say another level, it is say the third level. Okay, this is the fourth level, this is the fifth level, and then like this we have just quantized the sample. So we are getting this thing, then this 1 2 3, then this 4 5, this is dot, right? Okay, so this is 1, this 2 3, then this, sorry, and last one is like this. Okay, so this and this. Okay, so now if we quantized it, suppose this thing, we have quantized this thing into 8 levels, so total level is 8 levels. So 8 levels, so we can denote this by using some value. Suppose this 8 level, that is the 8 volt, that we are denoting by 111. The seventh level, that is the 7 volt, that is we are denoting by, suppose, 110. Then we are denoting by 101, 100, 011, 010, 001, and 000. These are the 8 levels. So if we quantize, then it has some information, that is we are just representing it using this 8 levels or using this 3 bit. So this is known as the digital signal. So we can use this 3 bit or some specific bits to represent this analog signal. Okay, so this is the main thing. So this we can say that this is the digital signal. This is the digital signal. So digital signal is discrete in time as well as discrete in amplitude. Okay, amplitude. Okay, yeah. And this analog signal, it is continuous in time, but discrete, sorry, and continuous in amplitude. Okay, continuous in amplitude. So we are using two basic things, that is sampling and quantization, to transform the analog signal to the digital signal. Okay, yeah. So let's move forward to the first question. So this is the first question. A 10-bit successive approximation type ADC uses a clock frequency of 1 megahertz. So what is the conversion time? So you should know that how the successive, so it's a very popular type of ADC. It is very fast in nature, that is very fast in nature, the ADC. So this ADC is known as successive approximation type, approximation type. Okay. So okay, sorry, it is not that much fast. Means compared to other ADC, it is faster, but it is not the fastest. Okay. Okay. So successive approximation type ADC, how it works? So ADC means we have to transform a signal, that is we have to represent an analog signal to its digital value. Okay, analog to digital converter. So suppose we have some analog signal which is VA. You can see in this diagram. Okay, this is VA. Okay, this is the VA. And then here actually in the ADC, this is the block DAC. We are using this as a reference. Okay, so this DAC, it has 4-bit DAC. Okay, 4-bit DAC, where D3, this is the MSB, and this is D0, this is the LSB. Okay, so what happens? So this 4-bit DAC converts this digital signal, suppose 1110 or 1101, any binary input, it converts to its equivalent analog value, and that analog value is V0 of DAC, and then it compares. So suppose we have a 4-bit DAC, so we can use it to perform a analog to digital conversion. Okay, so how this operates basically? So suppose D3, D2, D1, D0, that we are starting from 0 0. Okay, at first the value is 0 0, and then we are taking I equal to 3, that is we are setting the D3 equal to 1. So at first we are setting D3 equal to 1. So now the signal is 1 0 0 0. Okay, so then it will convert. Suppose this signal can detect from 0 volt. So this ADC can detect from 0 volt to 15 volt. Okay, 15 volt. So now how it will detect? See, so suppose this signal VA is, suppose it is suppose it is 9.5 volt. Okay, 9.5 volt. So how this will perform? See, so it is 9.5 volt. This ADC can detect from 0 volt to 15 volt, and so we have an analog signal 9.5 volt that we should detect. So we are using a 4-bit DAC at first. So at first what we are doing, we are setting the D3 bit to 1. So 1000 will be in the input of this binary input, and then it will convert it to a 4-bit DAC value. In the 4-bit DAC value, this converted to 8. Okay, so this, if we convert 4-bit DAC, so 1 into 2 cube. Okay, so that is 8 volt. So it is now 8 volt. So what happens? So if we, so the here we are using an op amp comparator, simple comparator. So if this positive terminal, that is V plus, and this is V minus, so comparator works like that. If V plus is greater than V minus, then output C equal to 1. Okay, otherwise if V plus is less than V minus, then C equal to 0. Okay, so now what happens? If VO DAC is greater than VA, that means V minus is greater than V plus, then C is equal to 0. Okay, and if the output C is equal to 0, that means so that so so here actually it will generate the 8 volt. Okay, so basically this 8 volt is less than 9.5 volt. Okay, so now the comparator output will be 1. Okay, because 9.5 volt is higher than 8 volt. So if that is 1, we are keeping that this D3 equal to 1. Okay, so this D3 bit equal to 1, and then we move forward. Okay, and then we will go I from I minus 1 and go to step 1. So this is the actually basically the algorithm, how it works. So I am just telling it in a more simpler way, that suppose at first we need to detect 9.5 volt. This ADC can detect from 0 volt to 15 volt, and the input is 9.5 volt that we have to detect. So at first we are giving D3, D2, D1, D0 as 1000. Now it will fed to the DAC, and the DAC convert it to the 8 volt. So 9.5 volt is greater than 8.8 volt. 9.5 volt is greater than 8 volt. So the output comparator is 1. So keep D3 as 1. Keep D3 equal to 1. So this is the first step. It completed. Okay. Now what happened? Now keeping the D3 equal to 1, we are setting this D2 to be 1. So D2 we are setting this to be 1. At first we are setting the D3 1, others are 0. Okay, now by keeping this D3 equal to 1, now we are setting D2 equal to 1, 0 0. Now it will convert this 1100 to its VO DAC, that is the analog value. So 1100, how much it is? 1 2 4 8. So 8 and 4 12, so it is 12 volt. So now this 12 volt is basically greater than 9.5 volt. So V minus is greater than V plus. So that means the output of C is equal to 0. So output of C is equal to 0. That means we will keep the D2 equal to 0. Okay, according to this algorithm. Now we will go for D1. So we are keeping this 1 fixed and 0 fixed. And now we will set the value of D1 to 1. Okay, 1 0. So now what is happening? So 1010 is the input. 1010 1010 means it is 10. Okay, so 10 volt, again it is greater than 9.5 volt, so the output will be 0, that is C will be 0. So then we will keep D1 is equal to 0. Okay, so D1 equal to 0. Now we will keep, so 0. Now we will set this as 1, D0 as 1. If we set D0 as 1, then what is the output? So here it is 1001. Okay, 1001, and 1001 is nothing but 9. So 9 volt is less than 9.5 volt, so the comparator output C will be equal to 1. So we should keep the D0 is equal to D0 is equal to 1. Okay, so finally the D3, D2, D1, D0 will be nothing but 1 0 0 1. So that will be the equivalent uh, digital conversion of the analog signal 9.54 in this special case. Okay, so how much conversion time is taking? So to set or reset the particular bit for a single bit, it will take one clock cycle. Okay, only one clock cycle it will take for to set or reset this thing. So for this 4-bit ADC, it takes total 4 clock cycles. 4 clock cycles. Okay, 4 clock cycles. Now in the question it is given like it is for 10-bit successive approximation type ADC. So 10-bit total it will take 10 clock cycles. 10 clock cycles. It will take 10 clock cycles. And the clock frequency is basically 1 megahertz. So clock frequency FC is basically 1 megahertz. So what is the time period of the clock? Time period of the clock is 1 by FC, that is 1 divided by 1 megahertz, which is nothing but 1 microsecond. Okay, 1 microsecond. And now the conversion time of the DAC, sorry, of the ADC, conversion time, that is T conversion, that is nothing but 10 time of 1 clock cycle, that is 10 clock cycles, right? So it will be 10 microsecond. So the correct answer will be option C, that is the 10 microsecond. So this is the way the successive approximation type ADC works. So here how many bits are there, that much clock cycle we need to convert the analog signal to the corresponding digital signal. Okay. So suppose there are n bit successive approximation type ADC, then we need total n into t clock this cycle. Okay. Yeah. Okay. So moving forward to the next question. So this was a pretty easy question. Okay. So the next type question is the number of comparator which can be accommodated on a single chip with a specific IC technology is 600. What is the maximum number of bits possible for a flash type ADC to make this ADC made using this technology? So here we are coming across another mode of ADC, that is analog to digital converter, which is known as parallel or flash type ADC. Okay, this is a 3-bit, as we have already discussed. So here how it operates, I am just telling it in a very brief way. So here is a voltage VR, which is the reference voltage given, and there is some resistance in the path of there. Okay, and the analog signal which we need to determine, that is being fed to all the positive terminal, that is the non-inverting terminal of the comparator. Okay, here we can see this is first comparator, 1 2 3 4 5 6 7, all the 7 comparator circuit we are giving this VA, analog input signal. Okay, and in the inverting terminal we are giving the reference signal. So suppose for here, what will be the value of VR? If we see, so what will be the value? So if we do simple voltage divider rule, V into R by 2 divided by the overall resistance, that is 1 2 3 4 5 6 R and 7 R. So this is 7 R. So here if we want to calculate here what is the value, so it will be VR into R plus 2, that is the 3R by 2 divided by total 7R. Okay, if we calculate here, it will be VR into 5R by 2 divided by 7R. It will be like VR into 7R by 2 divided by 7R. So like this it will happen. Okay, so you can see that this voltage is the minimum voltage and this voltage is the maximum voltage among all these voltages. Okay, so suppose any VA signal, so we have some reference signal value. So here what is the value? VR into R by 2, RR cancels out, so it will be VR divided by 40. Okay, so if the VA falls between any these two, suppose the value of the VA is like this, so this is the value of the VA. Okay, so so suppose here the voltage is like, it is the voltage, it is like, I am just saying 1 volt, this is the 2 volt, it is 3 volt, it is 4 volt, it is 5 volt, it is 6 volt, and it is 7 volt, suppose. And and this type of particular ADC can detect from 0 volt to 7 volt, suppose. Okay, and suppose this input signal is like 5.5 volt, suppose. Yeah, so 5.5 volt. So here we are using a proper voltage divider rule. Okay, so here we are getting 1 volt. So 1 volt is the input in the negative terminal and 5.5 volt in the positive terminal. So the output will be 1, because this positive terminal is greater than the negative terminal. Here also it is applying 5.5 volt and here is 2 volt, so it will be output will be 1. Here also 5.5 volt, but here it is the 3 volt, so the output will be 1. Here also 5.5 volt, but this input is 4 volt, it will be 1. Here also 5.5 volt and it is 5 volt, the output will be 1. Here also 5.5 volt, but this is the 6 volt, so it will be 0 because the negative terminal will be that. And then here it is 7 volt, and it is, sorry, it is 5.5 volt, and here it is 7 volt, so the output will be 0. So the output of C6 will be 0, C5 will be 0, and rest for others the output will be 1. Okay, so now we will use a special logic circuit, or we can say a encoder circuit, to encode this thing and to refer this thing in a particular 3-bit digital value. So this is how this special type of ADC works. Okay, so this is the basic thing, that how ADC work. So suppose if all the things are 1, then we can say the output will be 111. Okay, and if this C6 is only 0, then the output will be 110, suppose. And if the C6 C5 both are 0, that will be, suppose, we can say like 101. So this will be the output. Okay, so here, for in this case, this output will be 101. Okay, suppose this C6 C5 C4, or these three are 0, and the rest are all other are 1, so that will be converted to 100. So these are some logic circuit, special logic circuit, or some encoder circuit which can encode, and which can see that what are the status of the comparator, and based on that it will generates the digital binary output. Okay, so this is the basic thing of the ADC, and the one of the most important thing of this ADC is conversion time is very less. Conversion time is very less because all these comparators are working in a single clock. Okay, single cycle, means if we are giving this 5.5 volt input, at the same time this 5.5 volt input, it goes to each of the comparator circuit. Okay, and by calculating within a clock, means for a single clock, after a single clock, the output we can easily get. So basically this conversion time is nothing but t clock. Whereas in the previous case, it is n into t clock. Okay, n times t clock, and here it is only t clock. This is the conversion time. Okay, now we are moving to the question, that what is the question. So the number of comparator which can be accommodated on a single chip with a specific IC technology is 600. So what is the maximum number of bits possible for a flash type ADC to make made using this technology? So here we are using this 3 bit. So the output is 3-bit binary. Okay, 3-bit binary. Here it is 3-bit binary. So now what happens is, for 3-bit binary, we need 1 2 3 4 5 6 7. So here we have 7 comparators. Okay, 7 comparators means 2 to the power 3 minus 1 number of comparators we need. Okay, so now for it is already said, in a single chip the maximum number of comparators that can be accommodated is 600. So what should be the number of bit possible? Okay, so suppose we are doing 2 to the power 5 minus 1 comparator, so it will for 5 bit. Okay, so how much it is? 2 to the 5 minus 1, so it will be 31. Okay, so if we do 2 to the power 6 minus 1, that means it is 64 minus 1, that is 63, so it will detect 6 bit. Okay, 2 to the power 7 minus 1, so it will be 128 minus 1, 127, so it will be the 7 bit. 2 to the power 8 minus 1, so it will be 256 minus 1, 255, so it will be 8 bit. Okay, and 2 to the power 9 minus 1, so it will be 511, so it will be 9 bit. Okay, and then if 2 to the power 10 minus 1, so it will be 1024 minus 1023, so it will be the 10 bit. So that means to get a 10-bit proper digital binary output, we need at least 1023 comparator, but here we can only accommodate 600 comparator, so we cannot accommodate 1023 comparator, so 10 bit it's not possible. For 9 bit binary digital output, we need at least 511 comparator. So but here we can use 600 comparator. So among the 600 comparator, we can use 511 comparator to get the 9 bit output, binary digital output. So the correct answer will be option B, that is the 9. Okay, so this was pretty much easy thing. Okay, so this is how basically this comparator works. Okay, yeah. So now the next question, the full scale input of ADC is 10 volt. Full scale input means if we use the full scale ADC means analog to digital converter, analog to digital converter. That means if we have any ADC, we are giving some analog signal and we get some digital signal. Okay, yeah. So the full scale input means it can detect up to 10 volts, and the minimum resolution is required is 5 millivolt. So 5 millivolt is the minimum resolution. So what do you mean by minimum resolution? It is a very important thing. Minimum resolution, that means we can say this minimum resolution means the analog voltage that it can detect with changing one bit to the next higher bit. Okay, so I am simplifying this thing. Suppose 0 0, suppose there is a 3 bit ADC. Okay, and this 0 0 0 it refers to 0 volt. 0 0 1 it refers to suppose 0.5 volt. If there is 0 1 0, it can refers to 1 volt. 0 1 1 it will be 1.5 volt. 1 0 0 it will be suppose 2 volt. 1 0 1 it will be 2.5 volt. 1 1 0 it will be 3 volt, and 1 1 1 it will be 3.5 volt. So suppose this 0 volt is being addressed by 0 0 0, and this the next bit, next higher bit from 0 0 0, the next higher bit is 0.001, so it is 0.5 volt. So that means the resolution of this circuit is 0.5, because it cannot detect less than 0.5 volt. It can detect till 0.5 volt. Okay, so suppose you can see the difference between any two consecutive bit, remember this thing is 0.5 volt, the resolution, this thing is 0.5 volt, any two consecutive bit, it is 0.5 volt. Okay, so now in the question it is asked the minimum resolution required is 5 millivolt. So 5 millivolt is the minimum resolution required. So 5 millivolt is the minimum resolution required. Okay, so what is the minimum number of bits is needed for this ADC? How to calculate? That how much number of bits is required for this ADC? So the full scale input, full scale means if all the things are 1 1 1, all the bits are 1 1 1, then it can detect 10 volt. So 10 volt, suppose 0 0 0 indicates 0 volt and 1 1 1 indicates 10 volt. So this is the 10 volt deviation. Okay, 10 volt, and minimum we have to calculate 5 millivolt. So we have a certain step of 5 millivolt and then 5 millivolt and then 5 millivolt. By this gap we have to measure from 0 volt to 10 volt. So now how many bits are required? So total we need to find out how much levels are there from 0 volt to 10 volt, right? So suppose this ADC full scale input, that means suppose it is a 4 bit ADC, okay? In the 4 bit ADC, so 0000 that refers to 0 volt, and then 1111 that refers to 10 volt, suppose. So here what is the resolution? If the question is asked, what is the resolution? So how you can determine what is the resolution? So that means this full scale, this voltage minus this voltage divided by how much levels are there. How much levels are there? 2 to the power n minus 1 levels are there, right? So here how much level is there? 1, 2, 3, 4, 5, 6, 7. So 2 to the power 3 minus 1, that is 7 levels are there, right? 7 levels are there. From 0 volt to 3.5 volt, we moved by 7 levels. 1, see, I am drawing it in another color. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So this is the full scale voltage because all the inputs are 111 and the corresponding output is 3.5. So this is the full scale voltage and this is the minimum voltage, 0 volt. So and within this 0 volt to 3.5 volt there are 7 levels for here, that means 2 to the power n minus 1. 2 to the power n means n is the bit, here 3, 2 cube minus 1, 2 cube minus 1, that is 8 minus 1, that means 7 levels are there, okay? So we have to divide this full scale minus the 0 volt into the 7 levels, okay? And then from there we can easily determine that how much ADC is required. So here in this particular question, how to solve this? The full scale voltage of ADC is 10 volt, so it can detect from 0 volt to 10 volt, okay? Full scale means all the inputs are 1, we don't know how much bits are there, and this 0 means all the bits are 0, we don't know how much bits are there. So now this 0 to 10 volt we have certain levels. So it has a step of 5 millivolt, that means it has a resolution of 5 millivolt. It can detect the next point 5 millivolt. Next it can detect 10 millivolt. Next it can detect 15 millivolt, like that it will detect, and finally it will detect 10 volt, okay? So how much levels are there? So total number of levels equal to 10 minus 0 divided by 5 millivolt. So 5 millivolt, so that means 10 divided by 5, if we do, how much it is? I am using the calculator. 10 divided by 0.005, okay? So here it will be 2000. So here it will be 2000 levels. 2000 levels are there. So how much bit it will get? So the 2 to the power n minus 1 is 2000. So 2 to the power n equal to 2001, and now we know that 2 to the power 10 is 1024 and 2 to the power 11 is 2048, right? So minimum 11 number of bit is required to consider this 2000 level, right? Because using this 10 level we can consider 1024 minus 1 means only 1023 level we can get, but to get 2000 level we need 11 bit. Using the 11 bit we can get at most 2047 levels, among that we need 2000 levels, and using this thing we can get this thing, all right? So 11 bit is minimum required. So what is the minimum number of bits required for this ADC? It is 11. If you use 12 number of bits uh, in the ADC, then also you can get this minimum resolution, right? But we are in the question it is asked what is the minimum number of bits. The minimum number of bits is 11, because using 10 bit we cannot get the resolution of 5 millivolt. Then the resolution will be much larger than 5 millivolt, right? Because we are then dividing this 0 volt to 10 volt into a big levels, right, into less number of levels. That means the level from the each level has a very high value. Okay, so that's the thing. Okay, the next question: a 10-bit DAC out gives an output VA equal to 2.5 volt for input this. What is the resolution? So this is very easy thing. So here now we are considering the DAC. Okay, so I am just discussing the basic thing of the DAC, that how the DAC works. So DAC, suppose this is digital to analog converter. So this is digital to analog converter. So here we have some digital signal as a input, and here we have some analog signal at the output. Okay, understood? Yeah. So now what happens? So suppose we have a digital signal 1011. So 1011 refers to, this is the binary, so it refers to 11. Now we are multiplying this by 0.1, multiplying this by 0.1, so it is 1.1 volt. We can, or multiply this by 10, 110 volt. So this is the digital thing. So digital to analog converter is nothing but binary to decimal value converter with a multiplication factor k. Okay, so you can say this 1011, that means 1 into 2 cube plus 0 into 2 square plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. That means we can say, so this is VDAC, digital to analog converter, is nothing but k, that means this multiplier, into di into 2 to the power I, where I equal to 0 to n minus 1, 0 to 3. N is the number of bit, k is the multiplier, n is the number of bits, and di is the corresponding digit, and we know that this I is starting from 0 to n minus 1. So this is the basically basics digital to analog converter. Okay, this is the basic things. Now here what is the question? That for input, if the input digital input is 0 1 0 0 0 0 0 0 0 0, then it gives the output as 2.5 volt. So what is the resolution for this 10 bit, right? So we can say that if it is 0 1 0 0 0 0 0 0 0 0, so this means this is 2 to the power 0, sorry, if you calculate this, 0 1 2 3 4 5 6 7 8 9. Okay, so this if we convert to binary to decimal value, then we'll get, so we have to convert this binary thing, that is the binary value, to the corresponding decimal value, right? So it is 2 to the power 8, that is 256. So this 256 is represented by 2.5 volt, right? 2.5 volt, 256, this value. So for to detect a single 1 bit, it has to detect 2.5 divided by 256, that much volt. So this is the answer, that what is the resolution of this? So it will be 2.5 by 256. So let me use the calculator. 2.5 divided by 256, which is 0.00976 millivolt, sorry, volt, which can be also referred to 9.76 766 millivolt. So the correct answer will be option A. So you understood, right, how we have determined. See, one more thing, one more way you can solve, you can also think this thing, right, that suppose all the these digital bits are 111. Okay, so 11 1111 1111. So now what is the corresponding decimal value? So it will be 1 into 2 to the power 9 plus 1 into 2 to the power 8 plus 1 into 2 to the power 7 plus 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 1 into 2 to the power 4 plus 1 into 2 to the power 3 plus 1 into 2 square plus 1 into 2 to the power 0, right? And that is equal to 2 to the power 10 minus 1. Okay, and 2 to the power 10 means what? 2 to the power 10, that means 2 to the power 10. So this is 1024 minus 1 means 1023 levels are there. Okay, so it can detect from 0 volt to 1023 volt. You can say like this also. Okay, say like this also. Now if the resolution is 1, then only 1 volt. If the resolution is 1 volt, that means we can say in other way that 0 to 1023 levels, these levels, that means total 1024 levels are there. Okay, 1024 levels are there. So among these, if this 256 level is denotes from 0 to 2.5 volts, so for a single level that will denote 2.5 divided by 256, which is 9.766 millivolt. Okay, so that is the answer. Yeah, the next question. For the DAC in question 4, the same question, let the output voltage VA1 corresponding to this input and at VA2, and the VA2 is this. So what is VA1 minus VA2? So VA1, so we know the resolution is nothing but 9.766 millivolt, 9.766 millivolt. That means it is the it is the difference of the two levels, two consecutive bit, right? If there is 0 0 0 0 0 0 and 0 0 0 0 and there is 0 0 0 0 0 0 0 1, so these two level difference in the analog, it is 9.766 millivolt. So now here VA1 is corresponding to this. So VA1 is what? VA1 is equal to, so this we have to calculate in decimal value and then multiply with this level, so we will get that corresponding analog voltage. So this thing is, so 0 1 1 0 0 1 and 1 1 0 0. So that means this is 0 1 2 3 4 5 6 7 8 9. So it will be 1 into 2 to the power 8 plus 1 into 2 to the power 7 plus 1 into 2 to the power 4 plus 1 into 2 cube plus 1 into 2 square, like this. Okay, 2 to the power 8, like this. Okay, and the second thing, this is the so the VA1 will be 1 into 2 to the power 8 plus 1 into 2 to the power 7 plus 1 into 2 to the power 4 plus 1 into 2 cube plus 1 into 2 square. This thing multiplied with 9.766 millivolt. That much millivolt is the VA1, right? For VA2, VA2 is what? Now this VA2 is nothing but 0 1 1 0 0 0 1 0 0 0. So this is 0 1 2 3 4 5 6 7 8 9. So it will be 1 into 2 to the power 8 plus 1 into 2 to the power 7 plus 1 into 2 cube. Okay, so Va2 will be equal to 1 into 2 to the power 8 plus 1 into 2 to the power 7 plus 1 into 2 cube multiplied with 9.766 millivolt. Now we have to subtract these two, Va1 minus Va2. So Va1 minus Va2 if we subtract, so we'll get Va1 minus Va2 will be equal to, this thing will be cancelled out. If we take this common, this will cancel out, this will cancel out. So we will get 1 into 2 to the power 4 plus 1 into 2 square into 9.766 millivolt. So 1 into 2 to the power 4 is 16 plus 4 into 9.766 millivolt. That is 20 into 9.766 millivolt. Right? So that will be 20 into 9.766 millivolt. That is 195.32 millivolt, or you can say 0.195 volt. So the correct answer will be option D. Okay, so this was more or less easy problem. If you have a clear idea, you can easily solve this question. Okay, for a DSE of question 4, VA corresponding to input this is what? So this is the same thing. So we have 1 0 0 1 1 0 0 1 1 0. Okay, so now this will be 0 bit, first bit, second bit, third bit, 4 5 6 7 8 9. So if we convert it to the decimal value, corresponding decimal value, it will be 1 into 2 to the power 9 plus 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 1 into 2 square plus 1 into 2 to the power 1. So 2 to the power 9 means 512, 512 plus 2 to the power 6. So 2 to the power 9 is 512 and 2 to the power 6 is, it is 64 plus 32 plus 4 plus 2. So it will be 512 plus 64 plus 32 plus 4 plus 2, that is 640, right? 640. So the corresponding VA will be what? 614 into the resolution, right? So the resolution is, as we found out, 9.766 millivolt. So this will be into 9.766, this much millivolt, which is 5996.32 millivolt. So that will be 5.996 volt. So the correct answer will be option C, that is 5.996 volt. So it was too easy to solve this question. Now the next question, it is asked, what type of ADC is generally used in a digital voltmeter? So remember one thing, in case of multimeter, that is digital voltmeter, digital ammeter, we always use the dual slope integrating type ADC. Why? Because in the, we will discuss dual slope integrating type in the next problem, but I am just telling it in a very brief detail. Like in the dual slope integrating type, what we are doing, we are integrating the input. Okay, one first time we are integrating with respect to the analog voltage, and next time we are integrating with respect to the reference voltage. So as we are integrating, and if there is some noise, suppose if there is some noise, so immunity to noise of this dual slope integrating type ADC is the most important thing. That is, immunity is very high. That means if there is some noise, that will be cancelled out as we are integrating the input, right? So that's why in the digital voltmeter or any digital ammeter, or basically in the digital multimeter, we use generally dual slope integrating type ADC. It is a very slow, convergence is very slow, but it gives a high accuracy. High accuracy means why? If there is a noise, then that will not be detected, but means that will not affect the output. Okay, so this is the thing. So I will discuss the dual slope integrating type ADC in the next few problems. Okay, in the next problem. Okay. Okay, see, the circuit shown in the figure is DAC with input S3, S2, S1, S0. Okay, so there are different things, like here we have the input S3, S2, S1, S0. So you have to see that this circuit is basically the R2R ladder circuit. R2R ladder circuit. This is a special type of digital to analog converter. Digital to analog converter. Understood this thing? Okay. Digital to analog converter. Okay. See this thing, very important. Okay, if you don't have any concept regarding this R2 or ladder circuit or this type of DSC, then also you can easily solve this problem easily, because you know that how this op-amp works and how you can, it is a very basic problem of the op-amp, so you can easily determine without knowing that this is a R2 or ladder circuit. But it is better to know that this is a special type of R2 or ladder circuit, which is a special type of DSC, digital to analog converter. Okay, so now what is happening in in this figure, DAC has the input S3, S2, S1, S0. So this is S3, this is S2, this is S1, and this is S0. Okay, node AK is connected to the op-amp virtual ground. This thing is connected to the op-amp virtual ground if Sk is equal to 1. So it has certain value S3, S2, S1, and S0. If Sk is equal to 1, then it is connected to virtual ground. That means it is connected to this thing. Okay, if S3 is 1, it is connected to this virtual ground. Otherwise it gets connected to the real ground. Real ground means this thing, real ground, and virtual ground means this thing. So we have seen this thing. So here is an op amp. We have already discussed this thing. So there are certain things over there. Okay, over there certain things, and mostly this is RF, the feedback resistance. So as I have already discussed, this op amp is an ideal op amp. This is the first condition, and the second condition is that there is some negative feedback. We can see there is some negative feedback. See, negative feedback, because there is an feedback path from output to the inverting terminal of the op amp. Okay, inverting terminal of the op amp. So that means this is a negative feedback. So if these two condition holds, then this op amp is in virtual short condition. Virtual short condition. We have already discussed this thing elaborately in the previous lectures. Okay, so virtual short means whatever is the voltage in the negative terminal V plus, the same voltage appears in the V plus. So V minus will be equal to V plus. So the virtual ground is a special concept of the virtual short. Okay, it's a special case of virtual short. That means now here V plus is equal to 0, it is real ground. So V minus will be also equal to V plus equal to 0. So this terminal is known as virtual ground. Virtual ground. Okay, so here that is the thing. It is given in the question that AK is connected to the op amp virtual short. That means this terminal. If Sk equal to 1, else is connected to real ground. What is the VO output if S3, S2, S1, S0 is 1001? So now we'll see 1001. So S3 is 1, S2 is 0, S1 is 0, and S0 is 1. 1001. Okay. 1001. So that means 1 means it is connected to op amp virtual short, this thing, and S0 is connected to this thing. But this 2 is connected to ground because S2 and S1 is 0 0, right? Okay, now what happens? See this thing. So here the VR, so this VR voltage is appeared over here, so it is VR. Now what is the voltage over there? Here what is the voltage? So if we see the so what is the voltage over here, if we want to determine, so we have to see the Thevenin equivalent voltage and Thevenin equivalent resistance over there. Okay, so what is happening? So VR is there, so these 2R and 2R is a parallel combination. See, this 2R and 2R is in parallel combination, so this 2R and 2R parallel combination makes a R in the series. Okay, R, this R and this R will make 2R, right? So it is 2R, 2R, and this 2R, 2R again in parallel combination, that will make an R over here. This R and R will make a 2R, and these 2R and 2R again make a R. Okay, R. So this, if this is VR voltage, here it has one resistance R, here it has another resistance R, so that will be VR voltage will be divided across these two resistance equally, that means this will be VR by 2. Okay, similarly if it is VR by 2, this resistance is R, so this VR by 2 will divide it across this and this equally, so this resistance will be this potential will be VR by 4, and this similarly this potential will be VR by 8. Understood? See, here it is VR, right? And till this thing it can be represented by a simply R resistance, so this VR is divided across these two R, right? So this will be VR by 2. Okay, simply the voltage divider rule. Okay, so this is the thing, this is the VR by 8. Okay, yeah. Now what is happening? Now see, which is connected to the virtual ground of the op amp? This S3, that means this VR is connected via 2R, and this VR by 8 is connected via 2R path. This S0, this is connected to the virtual short. So what is the current flowing through this? So here is one current, here is another current, so it is I1 and it is I2 if we say. So I1 is what? I1 is nothing but VR divided by 2R, and I2 is nothing but VR by 8 divided by 2R. Okay, so it is VR by 8 divided by 2R. So now the total current will be I1 plus I2, which is VR by 2R plus VR by 8 by 2R. Okay, and this current will flow with this terminal, and here it is 0 volt, right? So here it has certain drop, so V0 will be 0 minus twice R into VR by 2R plus VR by 8 by 2R. So this 2R and 2R cancels out, so equal to minus VR. If we take common, 1 plus 1 by 8, that means minus 9 by 8 into VR. Okay, and 9 by 8 means what? 9 divided by 8, that means 1.125, so minus 1.125 VR. So that will be the answer. So the correct answer will be minus 1.125. So it is one of the easy problem, because you, if you don't know that it is a R2R ladder circuit, then also you can solve this question by basic simple analysis of the circuit, basic Thevenin's theorem, or simply the parallel and series concept, and also the op amp concept. Okay, yeah. Next question. Next question. Sorry. In the DSC of question 8, what is VO when S3, S2, S1, S0 is 0, 1, 1, 0. So S3, S2, S1 and S0. This is 0, 1, 1 and 0. So what will be the thing? So here basically S2 and S1, these two are 1, 1 and rest of the things are 0, 0. So that means this is connected to ground, this is connected to virtual short of the op-amp, virtual ground, and this is also connected to virtual ground of the op-amp, and this is ground. Okay. So as I have already discussed, this VR appears over here. This is VR, and here we have then VR by 2. Why VR by 2? Again I am discussing 2R and 2R is parallel, so that will be replaced by R, and RR means 2R. This 2R and 2R is again parallel, so that means this is the R, and this RR 2R and 2R 2R is parallel, so that will be R. So that means VR again here R and here R, so it will be VR by 2. So similarly here will be VR by 2, half of the VR by 2, that is VR by 4, and here it will be half of the VR by 4, that is VR by 8. Okay. So now the current flowing into the op amp will be from this section and this section, that is VR by 2 minus 0 divided by 2R plus VR by 4, this is this potential, minus 0, that is ground, minus 0 divided by 2R. So that means 1 by 2R, if we take common, then it has VR by 2 plus VR by 4. Now this current should flow through this, because current cannot enter into the op amp, it is ideal. So here it will be plus, here it will be minus, so V0 will be 0 volt, means the potential at this voltage, minus twice R into I, that means 0 minus twice R into I is 1 by 2R. Here it has VR by 2 plus VR by 4, so that means 2R cancels out, minus VR if we take common, 1 by 2 plus 1 by 4, so minus VR if we take common, it is 2 plus 1, that is minus 3 by 4 VR, that is minus 0.75 VR. So it will be the answer. Correct answer will be option B, that is minus 0.75 VR. Okay. So this is the pretty much easy thing that we have already discussed, and now we will move to the next one. This thing, consider an 8-bit dual slope ADC with clock period of 1 millisecond. What is the worst case conversion time? Okay, so you have to understood how this dual slope ADC work. So it is dual slope ADC. Okay, it is a special type of ADC. So see one thing, so here we have an op amp, and here it is capacitor is connected across it, and here it is VO output, and here it has some VI input, there is a resistance. So simply if we analyze this thing carefully, it is minus, it is plus, here it has VI, here we have some resistance R, here we have one capacitance. If the switch is open, it is a capacitance, here is ground, and here is VO, here is C. So how to get the VO? So here it is a virtual ground concept hold, because it is an ideal op amp and it has a negative feedback, that means virtual short concept hold, V minus is equal to V plus, and V plus is equal to ground, real ground, that means V minus will be in virtual ground condition. Okay, so the current flowing through this will be I, this is I, the I will be Vi minus 0 divided by R, that is Vi by R. The same current will have to flow through this. So this I will be C d dt of dv dt. That means if the current is flowing through this, that means this potential minus this potential, that is 0 minus V0 divided by dt. That means that this equal to minus C dv0 dt. So this is the I. So these two I needs to be same because no current in flowing inside the op amp. So here it will be Vi by R equal to minus C dvo dt. That means minus 1 by RC Vi equal to dvo dt. That means Vo will be integration of minus 1 by RC Vi dt. That means minus 1 by RC, if we take common, it will be Vi dt. Okay, so this is the thing. So this is the thing. Okay, so that means this output will be minus 1 by RC integration of Vi dt. So whatever is the Vi, that will be integrated over the time, and that will be output. So how this dual slope ADC works? Suppose we have a analog voltage that we have to determine. This is the analog voltage. Okay, so at first we connect this switch with this VA. Okay, so what happens, it integrates and it's negatively in it has a negative value. So it will start from 0 and it will go through a certain time. Suppose certain time is t1, and after t1 it reaches a particular value which is known as the minus v1. Okay, this is minus v1. So what is the slope of this? The slope is basically, so here the input is now basically Va. So Vo is, we know, minus 1 by RC integration of Vi dt. Now for the first case, for the first case so for the first case this Vi is equal to Va. So that means Vo equal to minus 1 by RC integration over Va dt. So Va, if we take common, minus Va divided by RC integration of dt. So the slope is nothing but this thing, that is minus Va divided by RC. So this is written over here. And then again in the second time what happens, see, at t equal to 0 we have reset the, here what is it is written here, reset the integrator output Vo equal to 0 by closing S momentarily. Means S, if we close the S for a long time, then the output becomes 0 because it is a virtual ground, right? It is a ground, so it is ground, so it will also be ground. And then we just connect the Vi to Va, and this voltage need to be converted to the digital format. So whatever the voltage, input voltage, because it is basically a ADC, analog to digital converter, so whatever is the analog voltage, main analog voltage, so that is referred as Va, and it is basically a positive number. So what we are doing, we are doing the integration of this Va for a fixed interval time, which is t1. Here we have written already t1, and then at t equal to t1 the output reaches to a particular value, that is say v1, reaches minus v1. So minus v1 is basically minus Va by RC into t1, we can say this thing. Now what we are doing, we are applying a reference voltage Vr. So we are then applying a reference voltage Vr, which are basically a negative number, but it has a value greater than Va. That means the slope now, that will be minus Vr by RC, but Vr itself is a negative number, so it has a positive slope over there. You are getting it, right? It has a positive slope over here, and Vr has a higher magnitude, that means slope is very high, that means it is a very sharp slope. Okay, it will not take such long time like t1, but less than t1 time, that is t2. We are getting a t2. So we are waiting for until this slope, this value crosses the value of 0 again. Okay, reaches 0 again. So what we can say, this va is basically va into t1 by rc, and that is equal to mod value of vr into t2 by rc. So we can equate these two, and we can say t2 is basically t1 into va by vr. And now va and v are already fixed, because va we have to determine and vr is also fixed. That means t2 is a function of va. So whatever is the va, based on that we have actually we have the time t2. So based on the t2 we can say that va is high or low, or based on this t2 value we just encode this analog signal to a digital value. So in this digital dual slope ADC, what we are doing, a counter output which is proportional to T2 provides the desired digital output. Okay. So here actually it is a basic circuits of the dual slope ADC. You can see. So what happens? So basically it is a SPDT switch. Okay. So because this type of switch can be connected to single pole double throw. Okay, so it has a single pole, but it can attached with a also, a terminal also, b terminal also. So a terminal is va. So what happens, at first we reset all the things and the counter will start from 0000. Okay, and this single pole double throw switch is at position a, that means it is connected to va at first. Okay, now what happens, now this thing, see, so at first it was reset, but now this reset switch is off. That means it has a integrated circuit, as we have already discussed, already derived. So using this integrated circuit the vo is generated, and obviously vo is greater than this thing plus thing, so it is a basic comparator circuit. So as this is greater than as this is plus sign and this is minus sign, so here it will go to this and end it with the clock. So counter then counts up, because it will be high, because actually v0 is, we can see it will start from 0. At first it will start from 0, and then it has some negative value. So basically this v minus is less than v plus, and as it is less than v plus, the comparator output c, if we say it c becomes 1, and this 1 is ended with the clock. So whenever the clock applies, this is already 1, the value is already 1. So whatever the clock applies, based on that clock, the same clock applies to the counter and it will count up. So suppose it is counted from 0000, it will count to 0001. In the next cycle also it will integrate and it will go further negative and it will be 1. So like that it will happen. So it will count 0000 to till 1111. So 1111 count, and it will reach a certain value which is known as minus v1. Now what happens, whenever it reaches to 1111, at that time this overflow flag becomes 1, and then it will turn this SPDT switch to move from this position to b position. This position it will next move, it is the case 2, and the previous one is the case 1. Okay, so and this is the case 2, this is the case 2. So then what happened, so it is connected to vr. Now vr is positive, see one thing, positive. So that means this has some sorry, and vr is basically a negative value, and this output vo is some positive value. So this v minus positive value, it is always less than this. So again what happened, the counter again starts counting from 000 and stop counting when v0 crosses 0 volt, because now here vr is basically a positive value, but this vo, it will start to increase, right? So till now it is less than 0, and whenever it is greater than 0, then only it will generate 0 at the output, and that will stop the counter work. And then whatever is in the counter, that digital value is the basically the corresponding digital value of the analog signal. So in this way this works. Okay, this dual slope ADC works. So in this question, what it is asked? It is asked, for this 8-bit dual slope ADC with a clock period of 1 millisecond, what is the worst case conversion time? So we can see the conversion time is basically T1 plus T2. So T1 is basically 2 to the power n T clock, that is fixed because it has go from 0000 to 1111, it has to go and then it will stop, this thing, plus T2. Now what happens, suppose this VR value is generally put a negative and VA is generally a positive, and now we generally put VR value intentionally greater than VA so that it can converge quickly and we can easily measure. Okay, but if say suppose mod VR value is equal to VA value, this value, then it will say this T2 will take a same time as of T1, right? We have already determined this thing, right? That T2 is equal to T1 into VA divided by mod value of VR. So VA equal to VR, then T2 is equal to T1. That means this will be same as T1. That means 2NTC, and this is also 2NTC. That means 2 into 2 to the power n into T clock. That means 2 to the power n plus 1 into T clock. It is a worst case scenario. So the conversion time, it is the worst case. See. And now what happens? So 2 to the power, it is how many bit ADC? It is 8 bit dual slope, right? So 2 to the power 8 plus 1 means 9 into TC. TC is what? The time period of clock is 1 millisecond. So it will be 1 millisecond. 1 millisecond. 2 to the power 9 is 512. So 512 millisecond will be the answer. So the correct answer will be 512 millisecond. Okay. So see, it is a very slow ADC because its speed is very slow, as it takes 2 to the power n plus 1 into clock cycle. That is a huge, but it is a very accurate one also, because if it has any noise signal, then this noise gets cancelled because it is getting integrated. So that's why this type of ADC we generally used in the digital multimeter, that is digital voltmeter or digital ammeter, like that. Okay, yeah. So the next question, consider a 6-bit weighted register DAC. This is basically weighted register DAC. So how it operates? Suppose it is a reference voltage VR, and here it has some switch. Okay, suppose here it is S3, S2, S1, S0. There are some switch. Okay, yeah. So now what happened? So we can say that whenever the switch is connected to VR, then this terminal is VR. Otherwise, it terminal is when the S3 is 0, it is connected to ground. That means we can say that this terminal A3 terminal is connected to S3 VR. That means if S3 equal to 1, then it is VR, connected with VR, and if S3 equal to 0, if S3 is equal to 0, then it is connected to 0, right? Okay, then it is connected to 0, and this is S2 VR, this is S1 VR, this is S0 VR. So I will discuss briefly that how this weighted register DAC works. So suppose here, so this is basically R, and this is 2R, and this is 4R, and this is 8R, like this it happens. So here it is a 4-bit DAC, so that's why we have 4 different bits, that is S3, S2, S1 and S0, and here also it has R, 2R, 4R, 8R. Okay, so see, S3 is the MSB and S0 is the LSB. always see this MSB has to go through the lowest resistance. Okay, it has a corresponding lowest resistance, and this LSB has a highest resistance, that is 8R. Why? Because if this resistance is low, then only S3, if S3 is 1, it is VR. If S0 is 1, it is also VR. But here the VR divided by this low resistance path gives a higher amount of current. So the MSB should have higher amount of current compared to the LSB, and LSB should have the least amount of current flowing through it. Okay. So how it is operate? So see, it is a simple op-amp problem. So here what happened? The current flowing to the op-amp will be S3 VR divided by R plus S2 VR divided by 2R plus S1 VR divided by 4R plus S0 VR divided by 8R. Okay. So this is the thing, and how if we calculate this thing, how we will get, see. So now the VA will be, it is the 0 volt, and this current will flow through this. So here it will be plus, here it will be minus. So 0 minus I into RF. That means it will be minus I into RF. That means it will be minus RF into S3 VR by R plus S2 VR by 2R plus S1 VR by 4R plus S0 VR by 8R, right? So if we take 8R common, minus RF divided by 8R is equal to S3 into VR. If we take common, S3 into 8 plus S2 into 4 plus S1 into 2 plus S0 into 1. So we can write minus RF, sorry, minus VR minus VR divided by 8 into RF divided by R into summation of k equal to 0 to 3 sk 2 to the power k, or we can write minus VR divided by 2 to the power k minus 1 into R, and here it is RF, here it is k equal to 0 to n minus 1, here it is also n minus 1, sorry, n minus 1, and it is sk into 2 to the power k. So this is the value. So see this thing, as I have already discussed, so DAC is nothing but basically binary to a decimal value converter with a multiplication factor k. So here it is the multiplication factor, which is k, and it is binary to decimal converter. Okay. Yeah. Now here what is the question? In the 6-bit weighted register DAC, 6-bit, here it has a 4-bit, okay, 6-bit, let R5 corresponding to MSB, R5 is corresponding to MSB, that is S5, so S5 is corresponding to R5, okay, and R0 is corresponding to LSB, so S0 it is the LSB and it is the MSB, it is connected to R0. Now what is the R5 by R0? So R5 divided by R0, so R5 obviously will be the less. If it is the value of R, then it has the value of, here it is, we can say 2 to the power 0, right? So here it will be 2 to the power 5 into R. So you can write R5 is equal to 2 to the power 0 R divided by 2 to the power 5 into R. So R cancels out. So this will be 2 to the power 0 by 2 to the power 5 equal to 1 divided by 32. So R5 by R0 will be 1 divided by 30. So this is the correct answer. Actually this question is wrong. It will be R0 divided by R5, because in the MSB always actually the resistance connected to MSB is always less than the register connected with the LSB. Okay, because it, if the register is less in case of MSB, then more current will flow. Okay, so the next question. So for the DAC of question 11, RF equal to R and VR equal to minus 5 volt, and all the resistances are exactly equal to the nominal values. So what is the output voltage of S4, S5, S4, S3, S2, S1, S0? Okay, so we have already discussed in the previous question that how to calculate the output VO, and we have reached the conclusion of this, right? VO, output VO, how to calculate this, and this is this thing. We have already said that this is nothing but the binary to decimal value converter, and this is the multiplication factor. So now we have to put the value and we have to solve the question. So it is telling like, let RF is equal to R, that means then what will be the V0 exactly for this thing. So at first we need to find out the summation of 0 to n minus 1 sk into 2 to the power k for this 100 100. So what will be the this thing? So here it is 0 1 2 3 4 5. So that means 2 to the power, sorry, 1 into 2 to the power 5 plus 1 into 2 square. That means it is 32 plus 4, that is 36. So it is the value of 36. So this value is 36, this value is 36. So now we can write that the output voltage VO will be minus VR into 2 to the power n minus 1 into R into RF into 36. Now RF and R cancels out because RF is equal to R, right? So it will cancel out. So minus VR divided by 2 to the power n minus 1 means 2 to the power n minus 1 means 2 to the power 6 minus 1, that means 2 to the power 5 into 36. And now the VR value is nothing but minus 5 volt. So minus of minus 5 volt divided by 2 to the power 5 is 32 into 36, that means 5 into 36 divided by 32. So how much it is? 5 into 36 divided by 32, it will be 5.625. 5.625. So the correct answer will be 5.625 volts. Okay, so this is the thing. Okay, the next problem. In the DAC of question 2 of the same, suppose all register have 2% tolerance, including RF and R, all the things. What is the maximum output voltage when this thing is 100 for the same thing, right? So you have already calculated that this value is 5.625. Okay, so for no tolerances, the VO is equal to 5.625 volt. 5.625 volt. Now the dependence is like that. We have VO is equal to minus VR. VO is equal to minus VR into 2 to the power n minus 1 R into RF into summation of 0 n minus 1 sk 2 to the power k, right? K equal to 0 to this. So that means RF and R has a very important role in this. Okay, so suppose it has 2%, what is the maximum output voltage? So VO will be maximum if RF is minimum, sorry, RF is maximum and R is minimum. So that means this VO maximum will be equal to 5.625, and now the RF has tolerances, so it will be greater value 1.02, and R will be minimum, that means it will be 0.98. Then what is the answer? The answer will be 5.625 multiplied with 1.02 divided by 0.98. The answer is 5.855. 5.855 volt. The correct answer will be option C. The next question, it is also the similar question in the DSC question 2. Suppose all resistors have 2% tolerance. What is the minimum voltage of this? The same thing. So the minimum voltage, so VO will be minimum if RF will be minimum and R will be maximum. So this VO minimum voltage will be 5.625 into 0.98 divided by 1.02. So 5.625 into 0.98 divided by 1.02. The correct answer is 5.404. 5.404. So the correct option will be option A. Okay. So this was the last question. So that's all for today. So we have successfully completed all the tutorial classes starting from week 1 to week 12. So I hope that you all enjoyed the course, and if you have any doubt further, then you can always mail me or post the doubt so that we can solve actually. So till then, goodbye. Okay, so I am ending the meeting, so let me stop the recording. Thank you all. It was very nice experience. Thank you. Bye.